Okay. Then I've got my lab list, and I'm going to start with the appendicular skeleton. And what I'm going to try and do with some of these pictures is I'm going to not only point out the name of the bone, but we're going to point out some of those surface markings that I'm likely to point to on a practical. And we can review a little bit. Everything in green here, the skull, the vertebral column, the rib cage, is all part of the axial skeleton. We got all the way through that last time, so we're going to pick up where we left off with the upper and lower appendages. And if we start with these upper appendages, we're going to include not only the forearm and the arm bones, but as well as this shoulder blade and collarbone, what we'll call the clavicle and the scapula. And then down here, the lower appendages, we're going to see the leg and the thigh are going to be attached to the rest of the axial skeleton by way of this hip bone, what we're going to call the coxal bone. And I've tried to pull these additional bins of bones out here. So there's plenty of them. You can just kind of grab some at random and take them back to your table whenever we get a chance to get our hands on these things. So these are all of the appendicular bones, arms and legs, and associated bones. We'll start with the upper appendages, and we'll look at this pectoral girdle. I think there is one model over here that shows us this pectoral girdle. That would be this one. You can see there is part of the humerus bone. There's the scapula and the clavicle and a series of ligaments that are holding these bones together. Remember, we said ligaments were bone-to-bone connections, and there is a few of those ligaments in this knee model that made the lab list. So we'll talk about a few of those ligaments right at the very end of the lab list. But back to introducing some of these bones of the appendicular skeleton. We'll start with this pectoral girdle, so we're going to include the humerus as well as these bones that attach the humerus to the rest of the body, this clavicle and the scapula. So we have several clavicles out. You should be able to notice the clavicle. And on your lab list, let me just see if I'm remembering this part correctly. We not only need to know the clavicle, but we have to be aware of either the acromial end or the sternal end. Is that true? Am I just making that up? Sternal end versus the acromial end. And if you look closely at this clavicle, you'll see that one end is kind of a little bit more flattened. You'll have to get your hands on it to see what I'm talking about. But one end is a little bit more flattened. That's going to be what we call the acromial end. You're going to see it's going to articulate. It's going to make contact with a certain part of this scapula bone, particularly this part of the scapula bone that's called the acromion process. So it starts to become redundant, and it starts to make sense that this acromial end of the clavicle makes contact with the acromion process of this scapula. So clavicle is our collarbone. There's our shoulder blade bone, or the scapula back there. The other thing we need to know on the clavicle, in addition to just its name, there's the acromial end, and then the other end is this sternal end that articulates with the sternum, in particular that manubrium of the sternum. And you can see this is a little bit more of a blunted end. So whenever you grab, I actually made this one of the bones on the station, you'll grab this clavicle bone, and when you flip it around, you should be able to identify the acromial end versus this clavicle end. Okay, so there's the clavicle. I pointed out that collarbone. Whatever. I won't make any Tony Romo jokes, but I'll stop. It's too old for that now, I guess. I'm over that. I'm over it. I've let it go. Anyway, back to the bone. So we talked about the shoulder blade bone or the clavicle bone. The next one on the list is, well, I was going to talk about the scapula next, and then we're going to end up going down the list here. Just naming the bones based off of their name. Then we're going to go look at each one in a little bit more detail. I had mentioned this clavicle or the collarbone. Then behind that is this shoulder blade bone that we're going to call the scapula. Then the arm bone we're going to refer to as the humerus. And then when we get down here into the forearm, there's going to be two bones in the forearm. One is the radius and the other one is the ulna. We're going to see pictures of them up close, but if I use this skeleton as an example, I'm going to lay it over my forearm. You can see there's two bones here in the forearm. One easy way to remember this is that the bone that runs between the elbow and then out to the thumb side of my wrist, that's going to be what we're going to call the radius. The ulna is going to go from the elbow to the pinky side. So in anatomical position, from elbow to the thumb is the radius. And you can also, if you can, notice how you can rotate your thumb around. You can rotate this radius. So 2 bones in the forearm. There's another clue that you'll notice. I'm going to leave it sitting over there. Instead, I'm going to come grab a random one from the box. You'll see this in the picture too whenever I pull it up. But the ulna is an easy to recognize bone because it's one of these things that has a U shape right there on the bone, kind of spelling the first letter of its name, this ulna. That U shape is made of a couple of different processes that stick out. We'll need to know those specific names. Radius and ulna, though, are in the forearm. Once we get to those wrist bones, those are the short bones. Those are all going to be collectively referred to as carpals. And I'm going to come over here and grab one of these hand models. Or I could once again use this skeleton to show you the collection of carpals. We don't have to know individual carpal names on here. We just need to collectively know the wrist bones, all of those short bones, as carpal bones. Metacarpals are going to be the bones. These are long bones in the palm of the hand. They're covered up by the pad of the hand, the palm of the hand, pad of the foot. Then you've got your individually wrapped digits or phalanges. So either phalanges or digits will work for the individually wrapped bones. Now I said we would go back and look a little bit more detail at each one of those. The first one I was trying to point out by holding this clavicle bone up. We should be able to tell this more blunted sternal end from the more flattened out acromial end. In a two-dimensional picture, it might not be obvious, so be sure to grab this. From the clavicle, we're going to go back to the scapula, and this is also an easy to name bone because it's an irregularly shaped, well, it's a flat bone, but it's got a bunch of these irregular processes that stick off of it. And there are several things on the scapula that we need to know. So let me grab this lab list. In addition to scapula, we need to be able to find the spine of the scapula. And if I flip this scapula over, in fact, let me just use the skeleton so that you can see what we're talking about. I'm going to rotate this around to the back. There goes that. We're looking at the posterior side of this scapula, and there is a ridge that comes off of this posterior end. And if we follow that ridge all the way out, there is a flattened process. Let's see if this still works. Yes, so that flattened process is the acromion process. And then kind of looking at it from the very back side of the scapula, this is the posterior side of the scapula. You can see that ridge that's kind of raising up. And if we follow that ridge all the way out, there's that flat acromion process. So we're looking at it from several sides. We can barely see the acromion process here. Looking at it directly into what we call the glenoid cavity. This is, if I can grab a humerus bone real quick. We can see this is where the head of the humerus is going to fit into this scapula. It's going to be part of this ball and socket joint. So in reality, what these processes are doing is they're forming places for these ligaments to attach to. I'd held up this model just a second ago that shows you how many ligaments are attached between this acromial end of the clavicle and that acromion process, and then between these greater and lesser tubercles of the humerus and other parts of this scapula. So we'll need to know those processes that stick off of the scapula. That larger, flatter process is this acromion process, but then the smaller one that is a little bit more pointy, I'll grab this one. We're going to call this the coracoid process. So you have an acromion and a coracoid process. Together they kind of hold the head of the humerus in place. And we saw the head of that humerus kind of articulating with this smooth glenoid cavity. All of those are things that are on the list. We have to know the spine, we have to know this acromion process, we have to know that glenoid cavity where the head of the humerus articulates. There's that smaller process, this coracoid process. Then there are 3 fossa that we need to be aware of. A fossa is just going to be a shallow depression in a bone, and there's 3 of them we need to be familiar with. The names on the lab list tell you where they're located. One of them is the supraspinous fossa. If we find the spine and we find this little shallow depression in a bone just above the spine, this is what we call the supraspinous fossa. Just to see where we're going later on, I know I'm jumping ahead to muscles real quick, but we're gonna learn muscles called the supraspinatus and the infraspinatus, or the subscapularis. And these are muscles that are associated with these specific bone markings. So again, supraspinous fossa is above the spine, infraspinous fossa is below the spine. And then, so again, you have to look at the back side of this scapula to see the spine and the fossa above or below that. But if we flip it all the way over to the underside, this is the subscapularis. So the subscapular fossa would be kind of the interior side instead of posterior. This is more anterior side of the bone. Me holding the scapula from a distance is not helpful, so make sure that in lab time you grab and get your hands on this so you can find each of those structures on the scapula. Hopefully we've pointed those out, and I'm going to move on to the next thing on the list. Any questions so far about that? You may want to get your hands on it, so I'll try and get through these as fast as I can, and I'll just make laps when we get into lab time and come around and help point out all these things on the bones. So we're moving to number 3 on the lab list. None of those are new handouts. It's all the same stuff from last time. But this one that you were holding, we didn't get all the way through. There's that last page where we have to talk about the different types of joints and body movements. And the only other thing that I ran out of is the lab list for unit number 2. It's the same thing we've been going over the last couple of times. So if you have that, I'm just at number 3 on that unit 2 lab list. We're going through the appendicular bones. We left off last time when we finished talking about the vertebral column. We talked about primary and secondary curvature. And then we talked about true and false ribs. And then we left it there. So you're just in time. We're pointing out the names of the bones and then the specific structures on those bones from the lab list. And you'll see around the perimeter of the room I've set up a practice practical so that you can get an idea of how we're going to be asking these things Thursday, which is the real exam and practical. Interrupt me if you got questions about anything. Hopefully you're doing all right.
Is it called the funny bone because it's connected to the humerus?
Possibly. I don't know why, where the origin of the whole funny bone thing comes from. But it is true that funny bone in medial epicondyle, so that little medial epicondyle right there, that's usually when you hit that little funny bone. And what's interesting is there's an ulnar nerve that runs right in that little groove. So sometimes if you happen to hit that ulnar nerve, you'll feel kind of like this, what feels like when you hit the funny bone, that kind of shooting pain or needles or numbness or whatever that kind of goes through the rest of your arm. A little ulnar nerve right through that medial epicondyle. So humerus, right off the top of the list. We need to be able to recognize this bone here as the humerus. If it's just laying out on its own, and we can see it's the arm bone here on the skeleton. Recognizing it as the humerus is the first part. We need to know the other structures on the humerus. There is the head of the humerus. I'll try and hold this up. I know me standing in the front of the room isn't the best, but you can find this large, smooth, articular surface on this bone, which we're going to call the head of the humerus. Then there are 2 necks of the humerus, really where this smooth, articular surface stops. This is the end of what's truly considered the head of the humerus, and there is what's called the anatomical neck, really where that smooth articular surface stops, that anatomical neck of the humerus begins. But you'll notice there are these other structures next to the head of the humerus, these bumps. One of them is slightly larger. It's called the greater tubercle, and then there is a lesser tubercle, which is kind of hard to see from this picture, but if you hold the humerus up, you'll see just to the opposite side of the head, there are these 2 bumps, the greater tubercle and lesser tubercle. Those bumps are going to serve as places for ligaments to attach to. Again, it helps hold this pectoral girdle all together. You can see ligaments attached to that greater and lesser tubercle. There's a little groove in between the tubercles called the intertubicular groove. Did that make the lab? I think intertubercular groove must have slipped off somehow, but that's okay. I got plenty to point to there. Head of the humerus, we have to recognize the anatomical neck, which, can you see that little line right there? So that would be the anatomical neck. And then the surgical neck is really where the head starts to narrow and taper in. So they've just kind of drawn a little circle around this, what we call the surgical neck. So head, two necks, the anatomical neck and then the surgical neck. As we go down to the shaft of this humerus, there is a structure on the shaft of the humerus called the deltoid tuberosity. If you start to run your finger down the diaphysis of this bone, you're going to feel a rough patch. And again, just grab this humerus, start to feel down the diaphysis of the bone. That rough patch is what we're going to call the deltoid tuberosity. A tuberosity is just a rough patch on a bone, and that roughness of the bone makes it easier for muscles to attach to. And this tuberosity is a place where the deltoid muscle attaches, that shoulder muscle. So deltoid tuberosity is on the diaphysis of this humerus bone. Then as we get to the distal end of this humerus bone, we're going to go all the way down to the distal end, this elbow end, and we're going to see several structures that we need to know. Anywhere where there is a fossa, like the olecranon fossa, radial fossa, or coronoid fossa, hard to see on this screen, but those are going to be little shallow depressions, scooped out regions of bone. And we also know anytime that we see a process, that's going to be a little projection of a bone. I know we haven't yet looked at the ulna bone. The ulna bone is the next one on the list. But if you can look just for a second on the lab list, can you see underneath ulna where it says there are, and I'll just show this picture real quick. When we get to the ulna, I guess this is maybe the only place that we're going to see the ulna. We're looking at it face on right here, so it's not immediately obvious. Let me grab that ulna bone once again and show you from the side angle. When we look at this ulna from the side, we can see each of these little processes that stick up. That first process, kind of to use the shadow there on the board, this first little process is what we're going to call the olecranon process. That's the first thing on the list. The next one is the coronoid process. Together, the olecranon process and coronoid process are what kind of make up this U shape that tells us we're looking at the ulna bone. Now, both of those processes, the olecranon process and the coronoid process, if I can set that down for a second, when we watch this skeleton and we see how it flexes its arm, let me get this thing bent around the right way. When it flexes its arm or extends its arm, if you look closely what's going on at the elbow here, one of those pointy parts of the ulna, this coronoid process, is actually going into that coronoid fossa. It allows you to flex your arm all the way, or enable to extend, if you're going to extend your arm all the way. If you look around the back side of the elbow, you'll see that coronoid, I just said coronoid process, but I stopped myself. I'm looking at the back side of the elbow, so that's going to be our olecranon process up here. This olecranon process, when we extend our elbow all the way, or extend our arm out, that olecranon process has a shallow depression in this humerus bone that it can kind of fit into a little bit. It allows us to once again extend that arm all the way out. So this olecranon process, the little pointy part on the ulna bone, if I can come back here, it's going to make its way into this olecranon fossa when you extend the arm all the way out. So fossas are shallow depressions of the bone. There's one for the olecranon process of the ulna, and that shallow depression is on this humerus bone, so olecranon fossa. If we look at the other side, the opposite side of this distal epiphysis of the humerus, we can see this coronoid fossa. It's not quite as big as the olecranon fossa, but again, two shallow depressions. What we're talking about, this U shape of the ulna, that U itself is actually going to be biting down onto a specialized condyle. We said last time condyles are just these smooth articulating surfaces of a bone, and when we look at the distal end of the humerus, these condyles have been modified into one of them that kind of looks like a rounded ball shape. It gets the name capitulum. Then the other condyle has taken on this kind of trough-looking shape where it has a groove right down the middle of it. That particular condyle is called the trochlea. So at the distal end of the humerus, we should be able to recognize this rounded capitulum and then this trough-looking trochlea. The trochlear notch fits right into that trochlea. And you can see the coronoid process going into that coronoid fossa. You can see the olecranon process going into that olecranon fossa. That U shape is the trochlear notch, and it fits right onto the trochlea. So the trochlear notch is this part of the ulna bone, and the trochlea itself is this modified condyle on the humerus. And together they fit together. These smooth articulating surfaces of the bone are going to be these condyles. So the ulna articulates with the trochlea. We're going to see the radius is going to articulate with the capitulum. We're almost to the ulna and the radius. We're still talking about this distal end of the humerus. So those smooth articulating surfaces are the capitulum and the trochlea. If we go even further to the outside of these condyles, outside of the condyles are going to be what we call epicondyles, even further than the condyles. And the epicondyles in the humerus, there is what we call the medial epicondyle, also known as that funny bone. And then there's a lateral epicondyle, which is a little bony protrusion on the opposite side of the elbow. Maybe medial condyle is more noteworthy because it's commonly remembered as the funny bone, and I mentioned that ulnar nerve that runs right through that medial epicondyle. So sometimes triggering that can cause pain. Let's see how we're doing. We've pointed out all of the things on the humerus. I have pointed out a few of the things on the ulna already, so let's look at this ulna bone, one of those two forearm bones. And you can see how the radius is rotating on top of the ulna. Both of these articulate with the elbow. They articulate with the distal end of the humerus. But if we follow the radius, it's going to make its way at the very distal end towards the thumb, whereas the ulna is going to have an attachment point closer to the pinky at the distal end. There are some other things that are worth pointing out. I'm just going to jump all the way down to the distal end here to show you a couple of structures that are on both the ulna and the radius that I usually like to point out because it's interesting that when we start to name some of these processes of the bones, you'll have redundant names on different parts of the bones. For example, on your lab list, I don't know if you've noticed, but there are 3 different styloid processes that you have to know. We talked last time about the styloid process in this temporal bone. There's this brown temporal bone. There's that pointy little styloid process, and it was right next to this blunted mastoid process. So a reminder from last time, we needed to know temporal bone and then some structures on the temporal bone, like that styloid process. But what's kind of interesting is that there are 2 more styloid processes on the lab list, and they both can be found here in the distal end of the forearm bones. Notice how the radius over here and the ulna, they both have these styloid processes. I can just use the skeleton here. If you look at the distal ends of both of these bones, the radius and ulna have this little pointy-like projection called a styloid process. And what those styloid processes do, again, any projection on a bone is going to be a place for ligaments to attach these bone-to-bone connections. And in addition to those styloid processes, they kind of keep the wrist bones together. So there is a styloid process of the ulna. There's that styloid process of the ulna, and then there's a styloid process of the radius. What is also interesting, I'm just going to lift up one of these legs. Down here at the bottom of the leg, we can also see modifications at the ankle, where this fibula and this tibia have these processes that stick out and wrap around those ankle bones. Instead of calling these things styloid processes like we did in the wrist, they're going to be called malleoluses. So there's a medial and a lateral malleolus, but they're going to serve the same function, the same purpose as these styloid processes of the wrist. Anyway, we have to recognize ulna, we have to recognize olecranon process, this larger blunted process, the coronoid process, this trochlear notch. Opposite of this trochlear notch is where you would find the head of the ulna. The head of the ulna is where you find the styloid process. Again, head of the ulna right next to the styloid process. What else is on here? The only other thing I haven't pointed out is the radial notch. So on the ulna, there is going to be a notch for the radius. Here, I like coming back to the skeleton because it has all of the bones next to one another. If you come in, you look at how this radius rotates around the ulna. You'll see that the ulna is going to have a little groove for the radius. The radius is also going to have a groove for the ulna. If you can't see where I'm twisting this, up here close to the proximal end, you've got the head of the radius. There's kind of this obvious head and then a little tapered neck to the radius. This rounded head to the radius has to rotate, and there's a little part of the ulna right next to that coronoid process that's notched out. So when you grab this ulna, look for this radial notch. It's weird because the radial notch is on the ulna. And there is a ulnar notch that's on the radius. Down here at the distal end, if I go down here to the distal end, this is where you find the head of the ulna. Just like the head of the radius needs a little bit of space, the head of the ulna also needs a little bit of space for these bones to rotate past one another. And so part of the ulna is carved away to create a little ulnar notch. It's near the styloid process of the radius. Here I have grabbed just a random radius bone, and it's easy to see this kind of obvious head to the radius bone. There's the neck to the radius bone. I think this little bump, this rough patch on the radius called the radial tuberosity also made the lab list. Yes, and styloid process we already pointed out. So that ulnar notch is going to be, can you see that little groove or that little notch? Right in there. If you look at that distal end, that's where the head of this ulna is just kind of making a little bit of space. It's rotating around the distal end of this radius. Okay, so we should be able to recognize ulna and radius and a few of those structures on there. As far as carpals go, we don't have to know the individual carpal bones. Maybe this will be our example of short bones. Recognize those collectively as carpals. We'll recognize these bones kind of in the palm of the hand as the metacarpals. And then you have the individually wrapped phalanges. You could also use the term digits. Either would be acceptable. That takes us all the way out to the tips of our upper appendages. We're ready to transition into the lower appendages. All right, I'm going to make my way over here and grab some of these bones of the lower appendages. And it starts, in fact, I've got this whole thing connected right here. And the first thing that I'm holding on to, this hip bone, this is what's collectively called a coxal bone. We have a whole little bin of these coxal bones. And when you grab one of these things, there are several structures that we need to recognize on it. So I use the term coxal bones. Some lab list will call these things innominate bones. You're welcome to use the term innominate or coxal bones. One of the things on the lab list is this ala of the sacrum, and it's this little, I believe we pointed out that if you hung out in the lab last time, we were looking at vertebral column, cervical, thoracic, lumbar vertebrae. We looked at the sacrum, and then we looked at the coccyx down there. And there were some structures on the sacrum that we needed to know. And the ala was one of those structures on the sacrum. Anyway, the other thing was one of the auricular surfaces of the sacrum. And that auricular surface is what's currently making contact with this coxal bone. It seals together the sacrum and this coxal bone. So let's just look at one of these coxal bones. There it is on the screen. What this started out as is 3 separate bones. And it's now fused into one solid structure. And we can still refer to this solid bone as in terms of 3 different regions at least. This superior region is what we call the ilium. And there's this crest of the ilium that I don't know. Did I put structures on there? There is the iliac crest that we have to know. So the iliac crest is typically where your belt would go across. There is this little shallow depression that we can see as part of the ilium. This is the iliac fossa. And then there's another structure called the greater sciatic notch, and that would be this notch right there in the ilium. So that sciatic nerve is going to make its way right through that notch. Here's that auricular surface that I referred to. That rough patch is what seals together with the sacrum and makes that pelvic girdle. So ilium is the superior part. If you were to actually sit down, I'm going to grab these hip models right here to show us what I'm talking about. If I just were to set this thing down on the table, the part of this pelvic girdle that's making contact with the table is the ischium. It's in green here. And specifically the part that you're sitting down on is this rough patch, this ischial tuberosity. We've said the term tuberosity a few times already, and every time we've said tuberosity, we said it refers to a rough patch on the bone where muscles attach to. This ischial tuberosity is where those gluteal muscles attach to. So again, if you're sitting down like on bleachers or in a chair, you're sitting on this ischium. Then anterior to the ischium, there is this anterior part of the coxal bone that we refer to as the pubis. The connection of these 2 pubis portions of the bone are what form that pubic symphysis. We can even see a little bit of that fibrocartilage right there that kind of completes this pubic symphysis. In addition to knowing those 3 structures, I'm going to grab that lab list. There are a couple of other things. On the ischium, there's the ischial tuberosity. I pointed out the pubis, this anterior region. If we had 2 of those connected by a piece of fibrocartilage, this would be our pubic symphysis. So we were able to see that. The first 2 things are what I skipped over. If we were to hold one of these bones up, one of these coxal bones, there is this ball and socket joint where the head of the femur fits into. This cup-shaped depression is a structure on the lab list called the acetabulum. Now, we're still at number 9. I'll correct myself because, again, I'm from a small town where we might not say everything correctly, but I pronounce this thing acetabulum because I think that's how it's pronounced and that's how I spell it most easily. I've heard people pronounce it acetabulum, and you can say it however you want to say it. I don't care, as long as you spell it correctly. Acetabulum, acetabulum. It refers to this little cup-shaped depression on the coxal bone where the head of the femur sits right in there. It's going to form this ball and socket joint. In addition to the acetabulum, this structure on here, we have to know the foramen. A foramen is a hole in the bone, and this hole in the coxal bone is what we call the obturator foramen. Okay, and then number 10, you should be able to compare the pelvises to see the difference between a male and a female pelvis. And we've got a couple of them over here. I will randomly grab them because I don't know which one I'm grabbing, a male or a female. Looks like both of these are male. But let's compare what's going on here. If we hold up a male versus a female pelvis, like we can see on the screen, there are at least 3 differences that we can point out. In a male pelvis, it tends to be more narrowed and tall. So a more narrow pelvis versus a wider pelvis in females. You can see not only is it wider, it's more shallow. If you look at some of the bone markings, the ridges on the bones, the ridges tend to be more prominent in male skeletal system due to the higher levels of testosterone. So some of the bone markings are more extreme. I'll list 2 more differences. One of the most obvious differences is the angle down here of the pubic symphysis. If it's less than 90 degrees, this narrow angle, it tells you that it's a male. And we can see if it's a more shallow angle of 100 degrees or more, it is likely a female. So when I hold these up, Can everybody tell the differences between that pubic symphysis, looking at that angle? Over here it's much more narrow. This would be the male, and over here would be the female. Now if I take these things, we're just looking at it like we just did. If I take it and flip it this way, now I'm looking at each of you through this little hole of the pelvis. This rim, if I can get the coxal bone out of the way, this rim, this interior hole of the pelvis is what we call the true pelvis. In females, there is a much larger true pelvis, this inner circle, because this has to serve as a birth canal. In males, the true pelvis, this inner circle, is much more narrow. It doesn't have to serve as a birth canal. So that's what this line is trying to indicate. This inner rim is what we consider the true pelvis, and in males it is much more narrow than it would be in females. So a wider true pelvis. Should be 4 differences. And you know, on the lab list, I'm just going to have these things out where you'll have to tell which one is male and which one is female. So those would be good clues, unless I put some kind of lecture question in there. That might be good to know for lecture 2. There it is looking from underneath. You can just see a much larger true pelvis in females versus a much more narrow true pelvis in males. All right, now to the lower appendages. We just talked about those coxal bones, so we'll jump down to this thigh bone, the femur. Then we'll go down to what we call the kneecap bone or the patella. Then we'll talk about these 2 bones of the leg, and you can use this a couple of different ways. I remember there's 2 bones there in the leg. One of them is a little bone. Can everybody see how one of those bones is little and the other one is big, tall like a tower? Sometimes people remember this tibia bone because it's the tower-like bone in the leg, the tall one, versus the little bone in the leg. That little bone is the fibula. Tibia and fibula sound alike, but fibula here is the only one with an L. Tibia doesn't have an L, so that L tells me in my brain lateral bone. It's the little bone, and it's on the lateral side of the leg. The lateral side comes into play in just a second. So remember, fibula is the little bone, and it's also on the lateral side. Tibia, that's like the big tower bone. I guess you just have to remember tibia is going to be medial. Even though that might not be obvious, if you can always remember little bone is lateral, then by default, the tibia is going to be medial. Okay, and then when we get down into the ankle, we're just going to refer to those ankle bones as the tarsals. The bones covered up by the pad of the foot are the metatarsals, and then the individual toes we'll refer to as phalanges or digits again. But we'll start with this femur bone because there are some structures we need to see. Obvious on the femur is the head, and then you can see this narrowed neck just underneath the head of the femur. There are those larger protrusions called trochanters. There is the larger, greater trochanter, and then the lesser trochanter, which is just a smaller protrusion. In addition to those trochanters, we have to know the medial and lateral condyle, as well as the medial and lateral epicondyle, and then a structure called the linea aspera. I'm going to grab a femur. I thought I had one out here. This one's good. So I'm going to grab this femur, and I think I even have one of those femurs just as one of the stations on the practical. And when we grab this thing, we can obviously recognize the head and the neck of the femur. Right near the head and the neck is where you find those trochanters, a greater and a lesser trochanter. But as we make our way down the diaphysis of this bone, if you put your hand along not the anterior side, but the posterior side of this femur, maybe come grab the posterior side of this femur in the skeleton, you'll feel a ridge on this bone. That ridge going down the diaphysis of this femur is the linea aspera. So that's on the lab list. And as we make our way all the way down to the distal end, we can see these smooth patches of a bone. And by now, when we see a smooth patch of a bone, we're thinking a condyle. Grab my lab list. We have to know medial and lateral condyle. And one way that we can always tell medial from lateral condyle on here is the head tells you which side is medial. It's always pointing medially. So if we go back down here, this must be the medial condyle, same side as the head. And then opposite side of the head, this is the lateral condyle. So use the head as a reference point to tell you medial or lateral condyle. And then if this, I guess, Evelyn, I'm going to make you throw you on the whatever, not under the bus. I'm just using you as an example. Can you see those? Those are the smooth condyles. But if we go just to the outside, there's this little protrusion of bone that barely sticks out on either side of those condyles. Those little protrusions of bones are the epicondyles. They're not as obvious here in the distal end of the femur, but again, lateral epicondyle is opposite of the head. Medial epicondyle is on the same side as the head. So that's everything for the femur. Let's move on to the tibia. And I'm just going to use these. I'll hold this whole thing up. We're thinking of these two bones here in the leg. And again, one of them is tall like a tower. That's the tibia. And the other little bone here on the lateral side is our fibula. Let me catch up with the slides. Pretty good picture there. If we go all the way down to the distal end of these two bones, we can see those protrusions, those little bumps that instead of calling these styloid processes, in the ankle they're referred to as malleoluses. They serve the same purpose as those styloid processes. They keep the ankle bones together. In fact, this medial malleolus and lateral malleolus are going to sit down right on top of that talus bone. I can't remember if talus bone was ever on our list or not, but as we make our way down here into the ankle, this first bone kind of on top of the ankle is the talus bone. I'll show it to you from the other angle. Here's that talus bone, and those medial malleoluses, the medial malleolus and lateral malleolus sit on either side of this talus. Here's a picture of what I'm talking about. So this is the tibia. This would be the medial malleolus. There is the fibula. It's lateral, so that would be the lateral malleolus. And you can see all of these ligaments, these bone-to-bone connections that hold these bones together. The talus is kind of covered up there, and we can see exposed this heel bone, the calcaneus bone. There it is. Let's see. I'm going to go back to the tibia real quick. We have to be aware not only that tall bone is the tibia, we need to see the medial and lateral condyles on the tibia. So let me grab a tibia. And if we find this tibia and we start to search around the tibia, there is one spot right here at the proximal end of this tibia where we find these two smooth articulating surfaces of a bone. Smooth articulating surfaces tell us condyles, but we don't have a head on this one. How are we going to figure out medial from lateral condyle on the tibia? There's a clue there. Well, not on this. That would be the ulna. But there is a clue on the tibia. So up there at the very top of the tibia, if I were to take that bone from the screen and fold it down so that you could look at the top side of the tibia, you'd see those condyles. One is medial, the other one is lateral. Right now it's kind of hard to see at the very top of this bone, but if we come down to the distal end, there's the medial malleolus. There's not a head on this thing, but the medial malleolus tells you which side is medial. So if we go back up here, this would be the medial condyle on the same side as the medial malleolus. So the opposite condyle would be the lateral malleolus. So there's always a clue that tells you medial from lateral condyle. This medial malleolus, medial condyle. So we saw medial and lateral condyle. Medial malleolus was what told us medial from lateral. The only other thing on the tibia is the tibial tuberosity. And once again, a tuberosity is this rough patch on the bone. For the tibia, it's right on the proximal end of the tibia. This tibial tuberosity serves as a place for the patellar ligament to attach. That should be something that you remember because we're about to see that when we come over here and grab these knee models. This shows us some bone-to-bone connections. And I think there are at least 4 ligaments that we have to be aware of. We put down on the board last time, a ligament is a bone-to-bone connection. So right now, if I peel this thing back, we can see the patella. And the patella is connected to the tibia by way of this patellar ligament. And that patellar ligament is attached to this rough patch on the tibia that we call the tibial tuberosity. So on this model, we could also point to tibial tuberosity. Anterior side of the tibia, that rough patch where that patellar ligament attaches to. Okay, as far as the fibula goes, that is this little bone on the lateral side of the leg, and I currently don't have one set out for the practice practical, which means it has an even better chance of showing up on the real practical. There are, in this bin of tibias, they're mixed. Tibias and fibulas are all in that middle bin right there. Obviously, this is much skinnier than this tibia, so you shouldn't confuse tibia from fibula, but this fibula is lateral. We should be able to point out that lateral malleolus at the end of this fibula. What else do we need to know there? So you've got lateral malleolus. Opposite from the lateral malleolus is the head of the fibula. The head of the fibula and the lateral malleolus, they look kind of the same. The head is going to be a little bit more blunted, not quite as pointy as this lateral malleolus. You'll see it kind of like the styloid process. There's a much more of a projection down here at the distal end of this bone. Recognizing it as the fibula will be the first thing you'll have to do. Yeah?
What does malleolus mean? Is it biomechanical process? Is it just interchangeable?
So malleolus is just, it's kind of like in the humerus, whatever. In the humerus, we're calling these things tubercles, the greater and lesser tubercle. And then when we got down here to the femur, we were calling these bumps, instead of tubercles, we were calling them trochanters. But they're functionally the same. They serve as these rough patches for ligaments and muscles to connect bones together. So I think by using the terms trochanter, you know we're talking about the hip. We're talking about down here in the femur. When we're using the terms tubercle, we know we're talking about up here in the humerus. So that's why if we're using the terms malleolus, we know we're talking about the bones that hold the ankles together. And if we're talking about styloid processes, we're talking about those bones that hold the wrist, the carpals together. So they function the same. The term being different tells us a different region of the body, whether it's the wrists or the ankles. No problem. So I'm looking over the list. In addition to the tibia and fibula, I'm going to go back to this little picture there because that's the only one that has a picture of the patella. Maybe the skeleton up here is the best place to show us these examples of the short bones, those patella bones. I think I might have put one of those out on the practice practical. We said tarsals were the bones that are the ankle bones, collectively just called tarsals. And there are two tarsal bones we need to be aware of. This talus, which is like we said, the bone that the medial malleolus and lateral malleolus bite around. And then you've got this large heel bone, the calcaneus bone. All of the other ones we can just collectively know as tarsals. Then there are the metatarsals, the long bones covered up by the pads of the feet. And then we have the individually wrapped phalanges or digits, commonly called toes. So I think that takes us all the way through the lab list, but there is, there's another series of slides I need to jump to real quick. And the first few pictures of this second group of slides shows those structures on the knee model that we have to see. So there's just about 8 more things I need to point from the lab list, and then we just have lecture left. The last PowerPoint takes us into joints, and the first thing we'll talk about is the functional and structural classes of joints. But the reason that this is kind of grouped together with the skeletal system is because the skeletal system, we said it's big. One of the big advantages of the skeletal system is it provides protection against the soft, delicate internal organs. You can think of it as like a sheet of armor. And what's great about this sheet of armor is that it's solid protection for those internal organs. But the downside against this sheet of armor is that it is not very flexible. So if you can't make moves and get away, then it doesn't matter how good your armor is, you're likely to be doomed. So joints come in here because they provide flexibility in this coat of armor. Joints give the skeletal system ability to move. But what we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we will see, this ability to move comes at a cost. What we the joints are where there are weak parts in the skeletal system. Whatever. My brain works in weird analogies, and so I'm going to cut this part out. But there were these giant cicada bugs. You know those bugs that come out of the ground, and they live underground for years. And when they first come out, they actually don't have any wings, and they have to crawl to the top of a tree, and then they go through their first little molt, and they shed their exoskeleton. And then after they molt or shed their exoskeleton, they pop out their wings, and it takes about 20 minutes for these wings to kind of inflate. And then now they can fly around and try and find a potential mate. These are insects. They have a tough exoskeleton, so they've got some protection. But what you'll see, these cicada bugs, when they come out of the ground and they try and crawl up to the top of a tree, they're vulnerable to other insects. In fact, ants, it's not uncommon that you'll see these things crawl past an ant mound, and ants will try and attack these cicada bugs and kill and eat them. If you've seen ants attack these kind of insect warfare, what these ants will do is they try and put their stingers right into the joints of these larger bugs, because that's where the weak parts are. I guess I'm just trying to make the analogy that even in the insect world, wherever there are joints, those are the weak spots. That's where other insects try and attack. And we'll see that there are weaknesses in some of our joints. In fact, the thing that we're going to connect here is that the more movable a joint is, the less stable it is. There's this trade-off. The greater the range of motion, the less stable that joint will be. Maybe the joint that gives us the greatest range of motion is this ball and socket joint. It's also the least stable, the most likely to pop out of place. You have other joints like the sutures of the skull. These are immovable joints. So they rarely pop out of place. They're very stable because they don't have much movement at all. So there's always a trade-off between range of motion and stability. I'm getting too far into the joints PowerPoint already. What I wanted to start with at least is going through the parts of this knee model. And I have just a few pictures here that show us on the screen the things I'm trying to point to on this knee model. What we're looking at is basically the knee model that I'm holding up, except the knee model I'm holding up doesn't have any muscles attached to it. But you'll notice how part of this model is just kind of flopping around here. If I pull this flopping structure back, you can see the patella. In fact, if I just go to the next slide, it's kind of what we've done. We've cut this tendon that went to the quadriceps muscle, and we've kind of peeled it back so that we can see the patella. Same thing that I've done here. I've cut, this would be the tendon that was going up to the quadriceps muscle, and we've peeled it back. Maybe just to take a step back, again, a bone-to-bone connection we said was a ligament. So this is our patellar ligament between the patella and the tibia. But anytime we have a bone-to-muscle connection, a bone-to-muscle connection is a tendon. So this is going to be the tendon of the quadriceps muscle. So the part of this model that's cut, and I know it's all the same color, but if you look close, Evelyn, here's where I'm putting you on the spot again. Can you see where those fibers get a little bit larger, kind of right there as we go up? And then down there a little bit smaller. You got to look close, but as those fibers get larger, this part is representing the tendon of the quadriceps muscle. And then beneath that, this part of the model is the muscle to bone connection, which is the tendon of the quadriceps. Quadriceps muscle, tendon of the quadriceps. Then we've got the patella itself. Beneath the patella, it's just patellar ligament, from the patella down to this tibial tuberosity. Okay, so that's the anterior part of this knee model. Let me peel that patella back so that we can see on either side of the patella there are these ligaments, again, bone-to-bone connection. You'll notice that one of these ligaments is going from the distal end of the femur down to this little bone, the fibula, on the lateral side. This ligament goes by a couple of different names. I think they're both on the lab list. You can either call this little ligament the fibular ligament, or it's also called the lateral collateral ligament. Again, fibula is on the lateral side, so fibular ligament or lateral collateral ligament is fine. There is a ligament between the femur and the tibia. So over here on this side, between the femur and the tibia, this is going to be our tibial ligament, or medial collateral ligament. Tibia is always on the medial side, so that's one way to remember that. Now look what happens if I peel this. I'm going to try and peel the kneecap back. You've got your tibial ligament and fibular ligament on either side. If I try and bend this knee all the way back, what it reveals in the center of this knee model, there are two more ligaments right on the kind of the middle portion of this knee. That's where we see our anterior and our posterior cruciate ligaments. If I peel this, if I kind of flex the knee and you look at it from the anterior side, there's two ligaments in there. The one that is more anterior, if you look at the model from the front, that is our anterior cruciate ligament. And the one that is more posterior is the posterior cruciate ligament. It's more along the popliteal region, that posterior cruciate ligament. But both of those are the ligaments kind of right in the middle of this knee joint. And when I had that thing peeled back, you'll notice that these articulating condyles are sitting on tops of additional cushions. These cushions are pads of fibrocartilage that get given the name meniscus of the knee. We have to know which one is the lateral and which one is the medial meniscus. Here we are. I've peeled back that ligament so that we can see here would be the condyles of the femur. These would be the condyles of the tibia, but we can't really see the condyles of the tibia because they have these meniscus that sit on top of them. The lateral meniscus is always on the side of the fibula because that tells us lateral. That's why I like that L in fibula. It always tells us lateral side, lateral meniscus. So then the opposite side would be the medial meniscus. Looking at it from the side, this again is just a side view that shows we've got the patella. Above the patella is going to be what we call the tendon of the quadriceps muscle. There's the quadriceps muscle. Here's the tendon that attaches that quadriceps muscle to the patella. Beneath the patella, it's just the patellar ligament. We've got a bone-to-bone connection. In the middle of the knee, we've got bone-to-bone connections. There is the anterior cruciate ligament. It attaches more anteriorly, and then the posterior cruciate ligament that attaches more posteriorly. I just wanted to show that from a few different angles. So that should be everything from the lab list in terms of this knee model. So now that we've made it through all of those lab list items, I'm going to catch up with the rest of the slides from the lecture. It's types of joints, structural classes of joints, and then body movements. Let's see how we're doing on time. Not bad, only an hour. Everybody doing okay so far? All right. Let's fuel up. We're doing good so far, and there's only one sketch that we have to put on the board, so there isn't a whole lot of things that we have to draw. Is it okay if I get rid of our to-do list? I'm just going to put a list of functional classes of joints and then structural classes of joints. It's currently up on the slide, but it won't stay there for long, so let's just put it on the board so that we can reference it. We'll say 3 functional classes of joints. Everybody still good? We're almost done with lecture. We need a break at all?
Yes.
We do. All right, we ready to get back into this just about? I think everybody's back. Good news, I think we've gotten all the way through the lab list. So you may all really be ready to maybe get your hands on some of these bones and trying to find everything from the lab list. We can break into groups and do all of that. I just have to get through one last little bit of lecture. And we'll start with functional types of joints first. This first one, to list these things out, the term synarthroses are just referring to joints that are immovable. Examples of these joints are going to be like the sutures of the skulls or the teeth sockets. These are joints that are bone-to-bone connections where they're not intended to move. So synovial joints are immovable joints. We'll see some examples of those. Amphiarthroses are kind of in between. They're slightly movable. So an example of an amphiarthrosis would be like this pubic symphysis. Typically when you're just sitting there writing notes, it's not moving. But in the event of childbirth or something like this, then this is a joint that can move slightly. So slightly movable is amphiarthroses, and then we're going to compare that to diarthroses like your shoulder or your elbow or your wrists or your fingers. These are all freely movable joints. So diarthroses just means freely movable. Again, in the lecture handout, I feel like there's matching sections where we have to match the functional classes of joints to their description, either immovable, slightly movable, or freely movable. Once we have those functions down, we're going to compare those to the three structural classes. What is the structural component that holds these bones together? If the structural component is some types of fibers, then it's a fibrous joint. If the connective structure is some type of cartilage, then it's a cartilaginous joint. We're about to see examples of those. The pubic symphysis I was just using, that's an example of one of these cartilaginous joints. We're going to see the sutures of the skull. Those are held together by tight little collagen fibers. That's an example of one of these fibrous joints. And then synovial joints are going to be the ones that we're going to try and draw. They are unique because of their presence of a synovial membrane. A synovial membrane secretes synovial fluid, and this is the fluid that lubricates the movement of those freely movable joints.
Can you say all of them again?
Sure.
Just the functional classes of the joints.
Yes.
Thank you.
So the functional classes are, there's only three. One class is synarthroses, which means immovable.
Okay.
Examples would be the sutures of the skull. So that's a bone-to-bone connection where those bones don't move. It's an immovable joint. A slightly movable joint and an amphiarthrosis would be like the pubic symphysis. It typically doesn't move, but in some circumstances, I gave childbirth as an example, where that bone-to-bone connection can move slightly.
Okay.
And then diarthroses would be freely movable joints. And these joints are lined with the synovial membrane that's going to secrete synovial fluid and allow the movements there to take place. So the wrist, the tips of the fingers, the knees, the elbows, the shoulders, these are all diarthroses. They're freely movable joints.
Thank you.
No problem. Now we're going to talk about what is the actual structural component that latches the two bones together. If the structural components are fibers, it's a fibrous joint. If the structural component is a piece of cartilage, like it is in this pubic symphysis, it's a cartilaginous joint. And if it's some type of synovial membrane that holds these things together, which I don't currently have a model of, I can use my elbow as an example of this, we'll see those freely movable joints being aligned with the synovial membrane. We're going to have to sketch that, so we're already lined up to do so. And I think you have this sketch that I'm going to do already in your lecture handout. We just have to label it.
On the lecture handout, it says, how you were just talking about the matching. For the synovial joint, it just says joint cavity present or bones joined by fibrous tissue.
So if we're talking about bones joined by fibrous tissue, it sounds like we're describing a fibrous joint. And what was the other one that you said?
Then the other one's synovial joints. It just says joint cavity present.
So if there's a joint cavity present, that's going to be describing one of these synovial joints.
Thank you.
And that's where we're going. So here are some examples of those. For example, we'll start with examples of these fibrous joints. There's not going to be any joint cavity at all. Most of these are totally immovable. Examples are going to include the sutures of the skull that I just pointed out, or was just using as a verbal example. Syndesmoses, this is going to be a joint in the ankle. And then gomphoses, these are teeth sockets. So let's look at sutures first. This functionally would be a synarthrosis. It's an immovable joint. Structurally, it's held together by fibers. So it would be a fibrous joint structurally. Functionally, it would be immovable. Synarthroses. So we said sutures of the skull are immovable, fibrous joints. This is the syndesmoses, this ankle connection. And we just looked at this earlier. We said this is the medial malleolus and there's the lateral malleolus. We've got this ligament that connects two bones. And when you're sitting there writing notes or listening to the lecture, this is an immovable joint. The tibia and the fibula are not moving, but if you were to try and run out of the building very quickly and run down the stairs, sometimes running up and down those stairs can cause this bone-to-bone connection to move slightly. So sometimes this one falls under the category of slightly movable. When you're just sitting there writing notes, it is not moving, so it's technically classified as an immovable joint. But again, held together by fibers, so it's an example of a fibrous structural joint. Another fibrous structural joint is these gomphoses. Gomphoses is just a tooth socket, this peg and socket bone-to-bone connection. There's the periodontal ligament, that's the fibers that holds these things together. Gomphoses is an immovable joint held together by fibers. So we've seen sutures, we've seen syndesmoses, that ankle joint, and we've seen gomphoses, the tooth sockets. The next structural group are cartilaginous joints, and we said these are any bone-to-bone connection that's held together by a piece of cartilage. I used the example of this pubic symphysis, which qualifies. I could have also used the other part of this model where we can see these two vertebrae. Where these two vertebrae meet, there's a piece of cartilage in between where these two vertebrae meet. So this intervertebral disc of fibrocartilage is also acting as a symphysis. Cartilaginous joint. We can even consider the costal cartilage of the ribs that attach those true ribs to the sternum. That's a bone-to-bone connection held together by a piece of hyaline cartilage. So synchondroses, that first part of it tells us an immovable joint, and then the second half tells us what is actually holding those two bones together, a piece of cartilage. So synchondroses, I'd already mentioned symphyses, the intervertebral discs, and that pubic symphysis, both are examples of these symphyses, bone-to-bone connections held together by cartilage that are slightly movable. Then the last one is a synovial joint, if I can get out of the way. Synovial joints are freely movable joints, and these bones, if they're going to freely be moving past one another, they have to have certain adaptations. And what we have on the screen is a typical synovial joint. I'm going to try and come over here and label the same thing that we have on the board. I just want to point out some key parts to it. And mention that all synovial joints are going to have these main parts, but some synovial joints have become highly modified. For example, the ones that we just looked at earlier, this knee model is a synovial joint that has become highly modified to support a lot of the body weight. So this particular joint have these additional pads that we called meniscus. That's an example of an adaptation to a specialized synovial joint. Not all synovial joints have to bear body weight, so we don't see meniscus in all of them. This is an example of a synovial joint, like the ones that you would find in between the tips of your fingers. So in my basic sketch of a synovial joint, I'm going to try and label all of the things that are on your diagram on the lab list. You should see in your diagram, well, I'm going to draw, we were drawing a long bone last time, and what I'm trying to do here is, I'm just trying to draw two ends of a long bone. Let's label this bone 1, and we'll label this bone 2. And we were drawing parts of the long bone last time, so let me take a second just to put some things on there that you might remember from last time. When we were talking about long bones, we said the ends of long bones were covered in this articular cartilage. I think we were putting that in blue. So articular cartilage we've got on the list. And then we also saw that to the outside of these long bones, connecting that articular cartilage and then running along the the diaphysis of the bone, there was that outer layer of connective tissue around bone. What do we call that? Periosteum, that's right. So this is periosteum. And if we wanted to go even further, we could have put that in the diaphysis is where you find that medullary cavity. And that medullary cavity, we said, was lined with an endosteum. Anyway, we don't have to get that far into it. We're thinking of this bone-to-bone connection. So let's add to that. I'm going to grab a new color, and we're going to draw, what's connecting these two bones is the presence of this synovial membrane. So from the articular cartilage of one bone to the articular cartilage of the other, let's draw our synovial membrane. This synovial membrane is what secretes synovial fluid. So maybe out to this side, I'm just going to label this as our synovial cavity. So synovial cavity with synovial fluid. That synovial fluid is secreted by this synovial membrane. So maybe I can just try and represent that with these dotted lines. The synovial membrane is secreting this synovial fluid, and that's going to be this pocket of lubricating fluid that prevents these bones from grinding together. This synovial membrane is a very delicate membrane that isn't really capable of holding these two bones together. So you'll notice your list has just to the outside of this synovial membrane, kind of running from the periosteum of one bone down to the periosteum of the next. Hopefully that's a different enough color. So just to the outside of that synovial membrane is what we call the fibrous capsule. So there's our fibrous capsule. It's just to the outside of the synovial membrane. Together, these two things are what we call the articular capsule. So the articular capsule, it's two things. It's the synovial membrane to the inside, secreting this synovial fluid, filling up that synovial cavity. And then just to the outside, there's the fibrous capsule. There's some collagen fibers there that are giving this some strength to hold these two bones together. Again, together it's the articular capsule. Let's see, the only other thing that we need to add to that, I'll grab this purple color. And we've already, we were talking about a few of these from the knee model. Anywhere where we've got a bone-to-bone connection, I'm going to go to the outside of that articular capsule. The most outside structures on here, these are going to be ligaments. Bone-to-bone connections are these ligaments. The picture that you have on your class handout, it's not one of the things that you have to label, and I'm trying to find a different color here. You'll see that on your diagram, you have to the outside of ligaments is where you have these muscles. So skeletal muscles are the things on the very outermost layer. So that's typical synovial joint. The next couple of slides will show us some specialized structures. Synovial joints, since we have these bones that slip past one another, they have to have this synovial membrane in between. And again, that's what makes the synovial fluid that helps prevent grinding of these bones together. When we look around the body to some of these synovial joints, like this ball and socket joint, there's a lot of movement there. And there are these additional synovial membranes that prevent muscles or bones from grinding together. One additional type of structure is called a bursa. A bursa is just a synovial membrane that has produced a little bit of that synovial fluid, and it's located in a place that prevent two bones from grinding together. This is actually part of the humerus bone, and this is part of the scapula, and what prevents those two from making contact is this synovial membrane called a bursa. Here it is. You can see the person in this picture is moving their arm back and forth, and no matter how they move their arm around, this bursa slips and it moves positions to prevent any bone from grinding together. So bursas are, like we said, synovial membranes that are located in places that prevent bones from grinding together. That little structure is a bursa pad. This slide just wants us to know that there is another structure that functions just like a bursa, except it's long and thin. Maybe where a bursa pad would be like a little, I don't know, maybe like a hacky sack of synovial fluid. We're talking about this little spherical, rounded structure that's filled with synovial fluid. That's represented of a bursa pad. If we wanted to compare a bursa to a tendon sheath, maybe this piece of paper would be more like a tendon sheath. It would be a flattened synovial membrane that has produced synovial fluid that wraps around a tendon. And it typically prevents that tendon from grinding against a bone. So they function the same way, bursa pads and tendon sheaths. They are only structurally different in that one is kind of a rounded pad where the other one is a elongated sheet-like structure. Again, bursa versus tendon sheath. So now that we've compared these types of joints, we can slip into the different types of body movements. So I'll demonstrate up here gliding movement, which is what you're doing with your wrist. If you're writing notes, you can see there's multiple ways you can move around your wrist. We'll talk about these angular movements. We're going to compare flexion versus extension versus hyperextension. We're going to compare abduction versus adduction. And then circumduction. We've talked about rotation before. And then there's a few special movements that we'll put on the list. We'll start at the top. I think the first one we said we were going to mention is this gliding type of movement. So gliding movements, like we saw in the carpals of the wrist, are where these two bones are just going to slide up past one another or slip over the other bone. It looks something like this. Those short bones there in the wrist are capable, you can move your hand front or back or side to side. You've got all these ranges of motions in this gliding movement. See if I have another, I guess I don't have another picture of the gliding types of movements. You've got bones just slipping right past the surface of other bones. So gliding movements are in the wrist. Angular movements are going to fall under the category of flexion versus extension. You can see this in the arms or in the legs. My arm and forearm are currently flat at about 180 degrees, as flat as I can possibly get them. And if I were to decrease this angle, it's currently at 180 degrees flat. If we went from 180 degrees to, say, 100 degrees or even 90 degrees, this is flexion. We're decreasing this angle. Maybe 45 degrees, so I'm still flexing this arm. Extending the arm is increasing that angle, so going from 90 out to 100 and then maybe out to 180, as flat as I can get it. Hyperextension would be past this 180 degrees, so I'm not going to hyperextend my elbow purposely. I've done it before and it's painful. So again, flexion is decreasing the angle. Increasing that angle is extension. And if you go past the maximum range of extension, that's hyperextension. Again, we could have used the leg. So my thigh and my leg are currently straight, and if I want to, so 180 degrees, and if I want to decrease that to just 90 degrees, I've flexed the leg, and then that would be extending the leg. Maybe the other way, or the other terms that are not as commonly used are these terms abduction and then adduction. Genesis, I'm going to use you as an example real quick. So she's writing notes, she's not paying attention, and if I were just to come over here and grab her arm and try and run off with her, I'm trying to abduct her. right? I'm pulling her arm away from the midline of your body. Hopefully I didn't pull too hard there. But that's fine. That shows you abduction is when somebody's trying to grab, the arm is going away from the midline of the body. So AB, abduction, is movement away from the midline. We'll talk about these abductor muscles in the leg and in the arms that move appendages away from the midline of the body. If instead of going away from the midline because somebody's abducting you, if you're moving these appendages back towards the midline of the body, this is adduction, adduction. So adductor muscles versus abductor muscles. And then circumduction is kind of a full 360-degree range of motion. So we're going to compare rotation to circumduction. And here's what I can rotate my arm, right? This is just 180 degrees rotation. I can do the same thing with my head. I can rotate my head side to side. This is rotation, just like this is rotation. Circumduction would be the full 360-degree motion. So I can't circumduct my forearm, or I couldn't circumduct my head. That would be spooky if I did. So circumduction is the full 360-degree motion versus rotation. We're about to see rotation in the next picture. This is showing abduction away from the midline and then adduction towards the midline. What this lady should be doing with her arm is the movement like this 360-degree circumduction motion. That is different than rotation. Like we said, rotation is just turning of a bone. So you can turn your head side to side, or we can turn our forearm from the supinated to the pronated position. I think we've used the terms supinate and pronate before, so that might be a reference. They're also using the leg as rotation. I can rotate my leg side to side, but I can't circumduct my leg. So turning of a bone is rotating it. I used just a second ago, pronation is when the palm is down and supination is when the palm is up. And if Evelyn's passing out soup and we've got our hand in the supinated position, we could pick up some of that soup. Supinated, pronated. You can also see those styloid processes sticking out from either the ulna here or the radius. But other special movements are going to include what we could either consider plantar flexion or dorsiflexion, and this has to do with pointing your toes. Imagine we're driving the car, and you quickly pull your foot off of the gas pedal. This is what we call dorsiflexion, so the foot comes up and off the gas pedal. As opposed to plantar flexion. Plantar flexion is when the toes go down. You're slamming on the gas pedal, or you're slamming on the brakes. The toes go down, that's plantar flexion. Dorsiflexion is the toes coming up. Okay, if we've got that down, we just got through basketball finals, but if you watched a lot of the basketball, it is not uncommon that you'll see these types of injuries when somebody's trying to drive into the lane. They can roll their ankle, and there's two ways that you can end up rolling your ankle, either an inversion, where the sole of the foot is what faces medially. Here's what an inversion looks like. It's more common that the ankle will get rolled so that your sole of your foot faces medially. All of your weight goes on the lateral side of the foot in an inversion. Eversions are also possible where the sole of the foot points laterally. You'd end up bearing all the weight on that medial malleolus, the tibia. Again, both can be very problematic. But inversion versus eversion, two different types of rolling the ankle, whether the sole faces medially or laterally. Protraction versus retraction. You can do this with the mandible, but you can also think of the tongue. This is a movement. You can protract your tongue or stick your tongue out at somebody. Or you can retract your tongue and pull it back into your mouth. This lady is going to do the protraction versus retraction example just with the mandible. So maybe if you really try and stick your mandible, protract it out there to exaggerate like an underbite or something, this is protraction of the mandible, and then retraction, I guess, would be pulling it back. Maybe the tongue is a good example of protraction versus retraction. And the mandible, another special movement that you can use with the mandible is this example of depression versus elevation. You can do this with the shoulders, so we can depress the shoulders or elevate the shoulders. So this is one type of movement, but you can do it with the jaw. Maybe somebody shows you some picture that's just blows your mind, and you end up with this jaw kind of dropping and your mouth is wide open. This is depression of the mandible. You're shocked. And then you gather yourself or whatever it is. Elevation of the mandible is just closing the mouth. So that might be obvious. One of the last ones is opposition. So we as primates have opposable thumbs. That puts us in a category with possums and one other mammal here that have opposable thumbs. But opposition, just having opposable thumbs, means that you can touch your thumb to the tips of your other fingers. So opposable thumbs. Okay, we've made it through body movements, and there's only 6 things left to point out. And this is the matching section, I think the last matching section that we have on the lecture part of the handout. It wants us to compare these different types of synovial joints and give examples of each of these 6 types. There was a review sheet that was produced by one of our groups, and it's a really good review sheet. It has just some pictures. It's additional study items if you want to label them. But I just wanted to point out, if you grabbed this, there's a page on here where it's showing these 6 types of synovial joints. And one of the things that's listed on this, they use the term ellipsoid joint. This textbook uses the term condyloid, but ellipsoid or condyloid are interchangeable. Just pointing that out in case you're looking at this sheet. There's 6 types of synovial joints. All of them are going to allow free range of motion. So let's compare these different types. The first one, plane joints, are joints that allow this gliding type of motion. So when we were looking at the short bones in the wrist, and we were talking about how these bones just kind of slip past one another, you can see this gliding type of motion. They allow movement in multiple directions, either side, front or back. So if you're writing notes, you can move your wrist around in multiple ways. That's our plane joint. So the next one on the list is a hinge joint. Let's see if we go in order. Hinge joints are the next ones. And these sound just like their name tells us. It's a hinge. So there's really just, I don't have this side-to-side motion. I've got really just this single plane of movement. I can either flex or extend. And that's all these hinge joints allow. I'm using my elbow as an example because typically these hinge joints are where you have one bone that has this cylindrical shape and the second bone has a trough shape, kind of just like this is our trochlea. It's part of the humerus. That's one of those modified condyles that looks like a trough. The other modified condyle right here is the capitulum. We're not really worried about the capitulum right now. We're thinking of this hinge joint, and that's a joint between this trochlea, and then right here is the ulna. Specifically, that's the trochlear notch of the ulna biting down right on top of the trochlea. So together that makes a hinge joint. You can see a cylindrical shape of one bone. That's the trochlea. The other trough-shaped bone is this U shape of the ulna. So hinge joints, think of the elbow, one plane of movement. Pivot joints. In a pivot joint, you've got 2 bones that are connected. One bone usually rotates within a ligament or some type of sleeve. And there are 2 that we've seen so far in our introduction of bones. One of them I was using in the forearm. We said the radius is able to rotate around the ulna. And if we look at how that radius and ulna are connected, this is the head of the radius. It's next to that U shape of the ulna. And what you really can't make out, well, you can barely make out, you can barely see a little bit of that blue articular cartilage that's on this part of the ulna. That's the radial notch. We said the ulna has a radial notch, and it's a little notch on the ulna that gives room. It allows for the head of the radius to rotate. So this head of the radius is going to rotate within this little sleeve. I was looking for another picture of it, but when we were talking about cervical vertebrae, the first two cervical vertebrae of the neck, the first one is an atlas, and it rotated around the second vertebrae, the axis. So the atlas and the axis is another example of one of these pivot joints. You got one bone that can rotate around the other. So the atlas rotates around the axis. It's what we use when you rotate the head side to side to say no to somebody. So when you're rotating your forearm, that's another one of these pivot joints. Okay, so we've seen three. Here is the condyloid joint, or sometimes called ellipsoid joint. These are going to permit angular movements. One example would be, maybe the best example, would be finding where your phalanges attach to the metacarpals. So if you're pointing your finger at somebody, look at how you can wag that finger around in multiple angular movements. So what's really going on here, if we look at these connections, there is an oval articular surface of one of these phalanges, the proximal end of this phalange, and another oval-shaped depression of your metacarpal bones. Here's a picture of what we're looking at. There's this oval-shaped distal end of one of these metacarpals, and then you can see there's an oval-shaped depression of one of those phalanges. Together, these two oval shapes allow the multiple angular movements, the kind of wagging around of your hand. So ellipsoid joint or condyloid joint, think tips of the fingers. Then that leaves only two more. There's a saddle joint, which is found in only one place. The thumb is where you find these saddle joints. If we look closely at these two bone connections, one has a concave shape, the other one has more of a convex. Here are the two shapes of the bone. You've got this concave shape that kind of sits down in this convex shape. What also kind of looks like a saddle, hence the name saddle joints. The thumb is the best place to give an example of this saddle joint. And the only other one we have to look at is right here in the shoulder. This is the ball and socket joint. In comparing all of these joints, this ball and socket joint has the greatest range of motion. It's the only one that you can do circumduction with. And like we said, the trade-off is the more range of motion you have, the less stable that joint is going to be. So ball and socket joints, the most freely movable synovial joints, so we said they're the least stable. They're described like their name. One rounded end of a bone that looks like a ball fits into a cup-shaped depression of another bone. The femur that we looked at sitting into this acetabulum is a good example of a ball and socket joint. The other ball and socket joint we have is between the humerus and the scapula. The head of that humerus sits right there in that glenoid cavity, which acts as the cup. The last few slides aren't pointing any structures out. It just reminds us that when you have these bone-to-bone connections that are not very stable, it is not uncommon that you can have excess stretching of those joints. So a sprain is when those ligaments that hold two bones together have been stretched or torn. Partial tears can repair themselves slowly, but if it's a complete rupture, this is only going to be repaired by surgery. So sprains, again, are going to be stretched ligaments. Cartilage tears, we mentioned earlier that cartilage doesn't have direct blood supply and it doesn't have direct nerve supply. So it's often not obvious if you've torn cartilage, and if you have, it very rarely repairs itself, like we said, because of the lack of blood supply. Often surgery is required to fix cartilaginous tears. We said dislocations occur when bones are forced out of alignment, and this can be common in sports or caused by serious falls. We said sprains are when those ligaments are torn or damaged, and that's usually followed by inflammation and stiffening of those joints, immobilization. Stiffening of joints is something that can happen in just normal living of life. If you're fortunate enough to live long enough, then you'll run into what's considered a normal wear and tear of using your bones, what's called osteoarthritis. there are many different types of arthritis. All of them have to do with bone that is getting damaged because it is grinding together. And in osteoarthritis, this is just kind of normal wear and tear on the bones. I don't know if I have a picture of it here. I'm just describing normal wear and tear of the bones. This is related to the normal aging process as you use your bones over the course of your life. What happens is that articular cartilage wears away. Eventually, the work of the osteoclast is going to outpace the work of the osteoblast. So your bones become a little bit more brittle. You lose that articular cartilage. Bones start to grind together and cause swelling and pain. So that's osteoarthritis, normal wear and tear on the bones. Rheumatoid arthritis is once again going to cause bone-on-bone grinding together, but this is not due to normal wear and tear. Osteoarthritis, which is the normal wear and tear form of arthritis, is different from this rheumatoid arthritis. In rheumatoid arthritis, it's an autoimmune disease where your body's own immune system goes to some of these synovial joints and it sees that articular cartilage and it confuses that articular cartilage as a foreign substance. And it tries to remove this articular cartilage. And it causes a lot of bones to grind together, scar tissue builds up, and that can lead to these bones actually fusing together. So this is an extreme picture of this rheumatoid arthritis. But that is the last slide of our joints PowerPoint. So we've made it through all of the PowerPoints for the skeletal system.